All right. When I'm recording this video, it is the end of March, beginning of April, and this time of year is the best time to observe galaxies. And so if you're doing this as part of a spring semester course, you're approaching the end of the semester, and it is galaxy season. And I just wanted to show you that. So here we are in sky view, and this is the southern hemisphere view of the sky. And currently the sun is up. If I go forward a couple hours, the sun is down. At the beginning of the night, you see part of our galaxy. The plane of the galaxy is this red line. And so these are going to be star forming regions, star death regions, globular clusters. If we go forward 6 hours, 1, 2, 3, 4, 5, 6, the plane of the Milky Way is kind of out of the way, and we have all this space up here, and in here we see galaxies. These things that are away from the plane, they're for the most part galaxies. In fact, the Virgo cluster is here. You see this cluster of galaxies, that's Virgo. And then if we go forward another 6, 1, 2, 3, 4, 5, 6, it's too far, the sun just rose. I'll back it up a little bit. You see the other side of the galaxy, again, globular clusters and star-forming regions, etc. So in the middle hours of the night, we have galaxies, and they're observable for long periods during the night. Okay, so you're about to pick your galaxy targets, and here's the Module 7 guide, and you go down a few pages, and you see we have a list of normal spiral galaxies, starburst galaxies, and Seyferts. And I'll explain what all these are in just a second. And these galaxies are both starbursts and Seyferts. We have some dwarf galaxies, ellipticals and lenticulars, and radio galaxies, which are pretty exciting. So different types of galaxies. And of course, not all of them are observable any time of year. You want to go to the observing guide and see what right ascension ranges are acceptable for this time of year. For example, for the beginning of April, you kind of want to be between 8 and 18 hours right ascension. So this would be no good, but these would be fine. You get the idea. Now, before you pick your galaxy, I'm going to tell you a little bit about galaxies. And then as a class, you should pick all different types. Make sure that across the class, you have at least one from most all of these categories. It's important that everyone doesn't do the same type of galaxy, because we're going to compare and contrast and better understand galaxy evolution. That only works if everyone studies a different type of galaxy. Okay. Now, let me just tell you a little bit about galaxies so you understand what these different types are, the general idea behind their formation and their evolution. So let me pull up an image here to get started. Yeah, start here. So this is a very famous image in astronomy. This is the Hubble Deep Field, or actually a more modern version of it. This is probably the Ultra Hubble Deep Field. The Hubble Deep Field was first shot, I believe, in the 90s. The idea was to pick a part of the sky where there's nothing going on, blackness, blank, nothing, and point Hubble Space Telescope there and image for a crazy long period of time, initially like 100 orbits, which is a super expensive observation to look at nothing. And then over time, they added to it. So here's the current result. And as you can see, they saw tons and tons of galaxies. Even though nothing was there to a bright level, you image faint, and the sky is full of galaxies. And these being faint galaxies, most of them are very, very far away. And we could try zooming in and you see more detail, but this isn't the best image. It's a little pixelated. So instead, I'll just zoom in. I think this region right here. Here's a zoom in of that. And you just see it's galaxy upon galaxy upon galaxy. And this is because, again, far away, light takes time to travel. So we're looking in the past, the very distant past. And back then, the universe was smaller. We all know the universe is expanding. That means back then, everything was closer together. These galaxies are close together. And because of that, they can impact each other. They can gravitationally affect each other. They can even run into each other. The space between galaxies is not too much bigger than galaxies. The space between stars in a galaxy is huge compared to the size of the star. So star-star collisions are pretty rare. It has to be a special circumstance. If you have two galaxies and you run them into each other, odds are no stars will collide. The gas, the giant clouds of gas in the galaxies will collide, but the stars pass right through each other and get all mixed up. But galaxies, so unlike stars, galaxies collide, they collide all the time. It's a big part of the formation and evolution process of galaxies. Okay. So out of this Hubble Deep Field, here's just some starting blocks. We call these pre-galactic fragments. If you look really, really far away, the faint stuff, we can measure the distance through their spectroscopic redshift. We get an idea for the distance. These are really far away, so they're much closer to the beginning of time than now. And again, we call these pre-galactic fragments. These are the building blocks of galaxies, small clumps of gas, basically. And since they're close, they would interact with each other. In fact, here you see a couple interacting, and here's a couple interacting. When they interact, whether it's a direct collision or just gravitational tugging as they pass each other, it destabilizes the clouds of gas, and they begin to collapse. And as they collapse, they fragment, and the fragments fragment, and they fragment. Eventually, you get a bunch of stars. And for young stellar systems, as we learned before, blue light dominates initially. And that's why most of these look very, very blue. You have an exception here, it's red, but maybe there's a lot of dust in that. Just speculating. But most of them are blue, indicative of ongoing aggressive star formation. And that's because the gas is being disturbed. Okay, well, how do we go from this to modern galaxies? It's a bottom-up formation scenario. The little things merge and form bigger things, and they merge and form bigger things, etc., until eventually you formed large galaxies, such as this one. And this is our sister galaxy, Andromeda. And we don't have a comparable picture for our galaxy, the Milky Way, because we've never gotten outside of our galaxy. That's a huge distance. If this were the Milky Way, the farthest probe we've ever sent is less than a pixel. Now, we haven't gotten very far, so we've never gotten outside of our galaxy to turn around and take a picture. But Andromeda is similar in size and mass, and so our Milky Way galaxy probably looks a lot like this. You may have seen T-shirts or posters with this galaxy and like a little arrow saying, "You are here." And you're not here. That's a whole different galaxy, but if it were our galaxy, we do live in the outskirts. Anyway, this is Andromeda. We live in the Milky Way, and these were assembled through the collisions of smaller components that grew bigger and bigger. Okay, here's a schematic of our local group. This is just nearby. Right here, we have the Milky Way. Over here, we have Andromeda. These are the two gravitational centers of our local group of galaxies. This group is bound gravitationally. And around these two big gravitational centers, you see all sorts of smaller things. Here's the large and small Magellanic clouds, which you can see from the southern hemisphere, and all these little tiny galaxies. We call them dwarf galaxies. And frankly, those dwarf galaxies are just leftover pre-galactic fragments. They're not too different from the original building blocks. They just haven't merged yet. They've been gravitationally pulled towards us, and so they kind of hover and orbit around us. Okay. But this is a complicated system gravitationally. Lots of things are pulling on other things. And occasionally one of these dwarf galaxies gets destabilized and in spirals into the larger galaxy. So here we have the Canis Major dwarf spiraling into the Milky Way. As it goes, it's left a trail of stars, and we found those stars and measured their chemical compositions, showing that they all had the same origin, and we measured their motions through space, and we can see that the purple stars are a single population. This is a dwarf galaxy spiraling its way in, entering the Milky Way, and it will bulk us up. Now, when this happens, a couple things happen. As that dwarf galaxy comes in, it disturbs the gas, both in it and in the Milky Way. And again, if you disturb gas, it collapses and forms stars. That enhances the blue light. You're forming star-forming regions. They glow in H alpha, pink. So often when we image these galaxies, we'll see little pink spots. Those are star-forming regions. And you also get dust. When you form stars, in the winds of these stars, they come off the massive stars, you form dust. So blue light, pink H alpha emission, dust, these are all indicators of star formation. And when something like this happens, it boosts those things. And so we go from being a normal spiral to what we call a starburst. We're still a spiral, but we're a star bursting spiral. We aren't at the moment. We're just a normal spiral. But galaxies out there, as they're undergoing this kind of process, can become starbursts. Now, another thing happens when the gas is disrupted. A lot of it will fall to the center of the gravitational well, the center of our galaxy. At the center of our galaxy, like at the center of pretty much every galaxy as we understand it, there's a black hole. And it's a pretty big one. Now, black holes form all over the galaxy. It's part of stellar evolution. Massive stars form black holes. And so some black hole is going to form at the center of the galaxy, but the special place, as galaxies get disturbed, gas falls there, it falls into the black hole, and they become more massive. The mass of the black hole at the center of our galaxy is 4 million times the mass of our sun. And that's not even special. That's just normal. Some get up into the billions. Okay. Now, what happens is that infalling gas will spiral around the black hole and through friction will eventually enter the black hole, making it bigger. But as it's doing this, it's really hot. It's hot gas. So you have charges going in a loop. Whenever you have charges going in a loop, you make magnetic fields in the perpendicular direction. So coming out of this black hole at the center, you have these magnetic fields, perpendicular. And some of the infalling stuff never makes it into the black hole. It gets caught up in the magnetic fields and shot out. Now, we've seen this before. It's hot gas, so it's ionized. It's charges. If charges get stuck in a magnetic field, they oscillate around the field lines, like we have here, and that releases synchrotron radiation. We saw this if you're on one of the teams that did Jupiter. You realize that we weren't looking at thermal radiation in our radio image, synchrotron. So here's a thermal spectrum typical of stars peaking in the optical or infrared or ultraviolet. Synchrotron radiation is very different. You can see it's much brighter down here at low frequencies, that's the radio, and also up at high frequencies like X-rays and gamma rays. But focusing on the radio, often the brightest things we see in the radio are synchrotron sources, and supermassive black holes at the cores of galaxies are one such source. Again, we saw this early on with Jupiter. This is a VLA interferometry picture of Jupiter in the radio. It's synchrotron radiation. So now we're going to see it in an extragalactic context, galactic and extragalactic. Okay. And so, when these little dwarfs spiral in and merge with the spiral, and gas falls down to the central black hole, and it feeds the jet, feeds the synchrotron, makes a radio source. And we only have single dish radio telescopes. We can't resolve it. Everything's super blurry, but we can detect radio coming from some galaxies. That tells you it's in an active phase, either a merger or an interaction where the gas has been triggered and falling into the black hole. And we call these Seyferts. If you have a spiral that's emitting radio waves from its core, it's a Seifert galaxy. And in the end, you just end up with a bigger spiral. It doesn't stay radio emitting forever. Eventually, the dwarf is absorbed and everything stabilizes, and so the black hole is not being fed, and you go back to being a spiral, just a little bit bigger. So it's a process. Okay. That's one way. That's a minor merger. Now, you can have stuff happen even if they don't contact. This is just an interaction. This is a great example. This is M82 and M81. These are galaxies you may pick to target. They're big, bright galaxies. M82 is on the left. It's the Cigar Galaxy, and on the right, you have Bode's Galaxy. And they're interacting. They're not just coincident on the sky. They're actually gravitationally interacting. And last time they swung by, it triggered a lot of star formation in the Cigar Galaxy in M82. Here's a zoom in of it. And so no collision, but the close encounter, the gravitational pull, caused the clouds to collapse, some of them anyway, which had a new round of star formation, and hence a lot of blue light. And when you have new star formation, the most massive stars, we learned previously, they live hard and die young. So within just a few million years, they supernova, which is a short time. Stars last billions. The massive ones last only millions. And so this happens, and then you have a whole bunch of high mass stars blow up all around the same time, cosmically speaking, that heats the gas and blows it out of the galaxy. And you can see this being ejected just from the heating from the supernovae. And that's glowing in H alpha because it's hot gas. So this is a starburst, but caused by interaction. Now, the big case is what happens when a big galaxy hits a big galaxy. Not just a little one hitting a big or two big ones interacting at a distance, but if they actually collide. And to figure out what happens, we just have to wait around because it's going to happen to us. In the local group, as I said, there are two mass centers, Andromeda and us, the Milky Way. And we've measured the velocity of Andromeda, and it's heading straight towards us. We're not going around each other. We're going straight towards each other. And so here's kind of a animation or computer simulation or combination of the two of what this will look like. So here's now, and Andromeda is this little thing way out here, but here's in 1 billion years and 2 billion. Imagine living here in 2 billion years. That's what the sky will look like. And then in 3 billion, we hit each other. And this is a head-on collision of major galaxies. It's going to trigger essentially all the gas. So not just a little bit, but all of it is going to collapse and form stars all at once. So very, very strong starburst. And then you have all the massive stars blowing up at once, like here. Like in our galaxy right now, we have a supernova explosion every 100 years on average. We're a bit overdue. But this, I don't know, every week, every day, I don't know. It'd be crazy when this happens. The sky will just be flashing with supernovae. This is what the sky will look like. Any gas that remains will be ejected by that. So you're just left with stars. And the massive ones, the blue ones are gone. So you're left with less blue, whitish stars, and it will just get redder with time. And that's what you see here. And since it was a head-on collision, the galaxies don't remain ordered. They don't keep their nice spiral structure. It becomes a train wreck, and they merge, forming something called an elliptical, which are kind of boring to look at. It's just a blob of white stars. Some can be interesting, as we'll see. The typical ellipticals are kind of boring. That's what we're going to become, and that's how they're made, colliding spirals. Okay. And, you know, they're going to remain this color and get redder because there's no more gas. So there's going to be no more new stars, no more new dust, no more new H alpha star forming regions. It's just going to be this old population of stars getting redder and redder. Again, we call this an elliptical. Now, before it settles down all the way to an elliptical, while it's doing the major merger, we'll also see radio emission from the center of the galaxy. You know, both galaxies have a black hole. Eventually they merge and become a single black hole, but they're going to be fed a lot. A lot of gas is going to fall down. And so you're going to have really, really strong jets and really, really strong synchrotron radio emission. Let me show you an example. This is Cygnus A. The gold in here is a Hubble image. I think it's a Hubble image. But anyway, you can see here, it's not the greatest resolution in this particular image, But you have a major merger of two spirals going on, and it's creating these jets, and they go completely out of the galaxy. There are jets in our galaxy. They're teeny tiny. You got to really zoom into the center to see them. But here, all the way outside the galaxy, and for it to be this strong, you're not talking millions of solar masses. You're talking billions of solar masses in the black hole. Even so, that's only a fraction of the total mass of the galaxy. It's not like a solar system where all the mass is at the center. These supermassive black holes are a small fraction of the whole mass of the galaxy, but here you're talking a billion solar mass black hole at the center, being fed because of the collision, creating these jets. And the red here is radio. Synchrotron emission, this is mapped with a very large array, an interferometer, so we can see detail that we're not going to see in our single dish images. When we image this with a single dish, it's just a big blur. We can measure brightness, but we can't see the detail. Okay. And so you get these double jets, and we call these radio galaxies. Now, if you're looking down a jet, straight into it, it can be incredibly bright. In fact, there's some relativistic effects because these jets are traveling a decent fraction of the speed of light. I think 20-ish%, if I recall correctly. That boosts their emission through relativistic effects and be very bright. We call that a blazar. And then eventually, when it settles down and there's no more gas falling down, the radio galaxy, the blazar, turns off, and you're left with an elliptical or a lenticular. Remember, spirals, you have ordered motion in a disk, but once they collide, you just have a messy blob. That's an elliptical. But sometimes some disk-like motion remains. It's like an elliptical in all of its other properties, but that little bit of disk-like motion, we call it a lenticular if it retains a little bit of disk-like motion. Okay, so here's a simple summary without the active galaxy part. So they're normal galaxies and active galaxies, like spirals, ellipticals, etc. Normal galaxies. When they're radio emitting, we call them active. So here's the simple story, leaving out the active part. Put that in a second. If you have a minor merger, spiral plus a dwarf, it just gives you a bigger spiral. If you have a major merger, spiral plus a spiral, you get an elliptical or possibly a lenticular. Okay. And here's the full story, including what's going on with radio emission from that central black hole. Here's a minor merger. You have a little galaxy here and a very tiny dwarf, and they interact, making a bigger spiral. But as they're doing it, you're going to get radio emission from the center, and so we call it a Seifert. In the optical, they just look like a regular spiral galaxy, but you look in the radio, you see a little bit of radio emission. And then when that settles down and turns off, you just have a normal spiral. But here we have a major merger, spiral hits spiral, and as it's getting all mixed up and feeding that black hole, you can have a radio galaxy, and much more powerful, the jets get shot out of the galaxy. Think of one of the jets, it's piling up so much gas as it goes, eventually it can't push forward anymore, so it stops and kind of poofs out, making this Q-tip structure. But eventually that ends, and there's no more gas to feed the black hole, and you become a normal elliptical or lenticular. So that's kind of the full story. The little addendum. What happens to ellipticals? Once you have an elliptical, what happens if something merges with that? And this happens a lot in galaxy clusters. So us in Andromeda, we form the local group, gravitationally bound, two large galaxies, bunch of small ones. But there are a whole bunch of local groups. We're just one of them that are all together as part of something called the Virgo cluster. So it's thousands of galaxies all organized into a bunch of little groups. We live in the outskirts of the Virgo cluster. And clusters are organized into superclusters. It gets bigger and bigger as you go until you hit large-scale structure of the universe. Anyway, this is a picture of the center of the Virgo cluster. Again, we live way off in the outskirts of this. In the center, it's a very busy place. You have a lot of galaxies in close proximity, and they will run into each other. And one galaxy is bound to be at the gravitational center, and things keep running into it. as it gets messed up, it initially becomes an elliptical, but then it absorbs more ellipticals and becomes a bigger elliptical. It absorbs spirals. If an elliptical absorbs a spiral, it's still an elliptical, but it will have a little bit of gas and star formation and dust from the spiral it's eating. And so it can get complicated. You can have ellipticals with spiral properties. And we would call these giant ellipticals or cannibalistic ellipticals. Again, they live in the centers of galaxy clusters and they're just gobbling up everything around it. They're messy eaters, so they may have some spiral features dribbling out of their mouths. Star formation and dust. Anyway, but they're often quite radioactive because they're always eating something, and that's feeding the black hole. Despite the few spiral properties, it's still very elliptical or lenticular in nature. In fact, this one right here is Virgo A. If I back up here, we looked at Cygnus A. That's one of our calibration sources. You may remember it. And this is Virgo A, another of our calibration sources. Here's a zoom in of that. That's taken with the Hubble Space Telescope. You know, it's just a blob, a white blob, so it's elliptical. But you can see it has a jet. And this jet's so powerful, you can even see it at optical wavelengths, higher energy. And so you have this jet coming out. So some central black hole is being fed. Okay, so now you know a little bit about the different types of galaxies and where they come from, how they form, how they evolve. And your next step is, as a team, to pick a galaxy to study in your final dark period of the semester. And again, every team needs to pick a different galaxy, and you want to cover as many of the groups as possible so you'll be able to compare and contrast and piece together a story of how galaxies evolve. We can't watch them evolve, but we can see them in different stages of their evolution. And that will be the capstone for this course. Okay, I'll stop there.